Here we go. We have a question: cut edge or bridges or critical edge. So this particular question has three different names, and in this question we're gonna check how many critical edges are there. So what is a critical edge? If I remove a particular edge, this will break down a graph into two different components. So if I remove this, it will not affect the graph. The component of this graph is still one. If I remove this, component is still one. If I remove this, component is still one. If I remove this, we have two different components. So till now we have critical edges as one. So if I remove this also, we have two different components. So our critical edge now become 2. If I remove this, so still we have one component only. Then if I remove this, we have one component. If I remove this, we have one component. If I remove this, we have three components. So we have three different critical edges. So now let's first read the problem statement. So we have this problem: critical connections in a network. There are n servers number from 0 to n minus 1. So this is a connected undirected graph, server to server connection, forming a network where A to B is a edge, represents a connection between A to B. Any server can reach to other server directly or indirectly. Critical connection is a connection, if removed, will make some server unreachable. So we need to return all the critical connections. So in this, if I remove 1 to 3 edge, so it will break down into two different components. So the only answer we have is 1 to 3 edge. So then we have another test case. In this, 0 to 1 is a edge. So if I remove 0 to 1 edge, it will break down into two components. So we have only one critical edge here. So now let's try to build the approach. So in this particular question, we have two different things. One is a discovery time, at what time in particular node is discovered, and then we have low. So low will contain the lowest discovery time to a particular node. So it will store the current low value or the neighbor low value. So we have a timer at what time this particular node is reached, this particular node is reached, this particular node is reached, at what time this particular node is reached. So our initial timer value is 0. So we have reached, we will start from 0. This is a connected graph. So we will start from 0. So I discovered this particular node at 0 time. Then I will go to its neighbor. So I will discover this particular node at value 1. Then one neighbor is 0, but 0 is already visited. How do we detect if this is already visited or not? So for every particular node, we have discovery or we have low. Initially, what I will do, I will assign infinity to the low value. So this is infinity, this is infinity. Every node contains low, and initially low is infinity. So this is visited because low is not infinity. So I will go to its neighbor. So our next neighbor is 2. Then I will visit this at time 2. Then we have two different things. This is a parent. I will not go to its parent. So in a function, I will pass the argument name parent. I will not go to its parent. I will just go to next neighbor. So I have this neighbor. Then this is already visited. So what I will do, so I will update my low at what time low is there. So neighbor low will be here. So instead of 2, I have 1, I have 0. So I have visited to all the neighbors. Then I have to check, is this a critical edge? If I remove this, can the graph be in two different components? How do we check? If and only if this, wait a second. So we have a formula for this. If and only if the low of neighbor, means at what time the neighbor node is visited. So low neighbor must be greater than discovery of current node. Discovery of current node. So let's write node here. So is the neighbor low. So this is 0, and the discovery time of this particular node is 2. So no, this is not a critical edge. So this is not a critical edge. Then we will backtrack. We come here. Then we will update its low to the neighbor low. So I will update to 0. Then we have to check, is this a critical edge? So what's the formula? If the low of neighbor 0 is 0 greater than discovery of this? No, this is not greater. So then I will again backtrack. I come here. This is visited, then come to non-visited. So we have this. At what time I will visit this? I will visit this at time 3. Then this is the parent. I will not go here, I will go here. So I will visit at time 4. Then the next neighbor is this. At what time I will visit? I will visit at time 5. Then this is parent. I will not go here, this is unvisited, I will go here. So I have 6 and 6. Then this is visited, so I will just update this. I will just update this. Then I have to check, if I remove this edge, can this break down into two different components? If the law of neighbor 4 is greater than 6, no, it is not. So we have checked this. Now just come here. We have, I will visit at time 7. So this is parent. I will not go here. I will not go to its parent value. So then I have this. So I will again backtrack to this value. If I break down this edge, can the graph be in two different portions? If the law of neighbor 7, so if there's a back edge or a cross edge, the law will be changed to the minimum value, but in this case law stays intact. So law is still 7. I will reach this particular node at low point 7, and discovery time of this node is 6. Yes, the law of neighbor 7 is greater than 6. So this is a critical edge. I will just add this edge to my answer. So I have this. So this is my critical edge. So let me write here, 6 to 7 is a critical edge. Then this is not my parent. So I have checked to this node. So then we'll again come back. So I have this. This is parent. I will not go here. So I come from this node. So I am coming back. I am doing backtracking. Is this law of neighbor 4, is 4 greater than 5? No, it is not. So then I will do the backtracking. So I have this. Is sorry. So I come from here. I missed one point, which is to update my low pointer. So I will update my low pointer. Then I have to check, is this a critical edge? No, this is not a critical edge. Law of neighbor is 4, which is not greater than 5, which is not greater than 5. So then I will again do backtracking and come here. So what's the value? Law of neighbor. What's the law of neighbor? Is 5. What's the discovery time of this node? This is 4. This is 4. So actually law of neighbor is 4, and discovery time of this node is 4. So law of neighbor is 4. This is 4. So this is not a critical edge. So then I will again backtrack. I am here. So if I remove this, can this break down into two different portions? Let's check. If the law of neighbor, yes, we have 4. It is greater than discovery time of this node. Yes, this is the case. So there's no back edge. If there's a back edge, it will just update it. But there's no back edge. So I can say this is a critical point. This is a critical connection. So I will add this. So I have 3 to 4 is a critical edge. Then I will again backtrack. I am here. Is the law of neighbor greater than discovery time of this node? Yes, yes. So this is also a critical connection. So 0 to 3. Why we write this, and why not we write this law of neighbor greater than law of node? Why don't this and this will work and this will not? So suppose I have this graph. So there's a edge. Discovery time of this is 0 and 0. Then I will go to this node. So discovery time of this is 1 and 1. This is parent. I will not go here. I will not go here. This is my minimum value. So the formatting, the ordering of edges is this, so then I will go to this particular edge. So I have discovered at time 2. Then this is parent, I will not go here. This is my neighbor, so I will just update my minimum. Then I have to check, is this a critical edge? If and only if low of neighbor, yes, 0, it is greater than 2, no it is not, so this is not a critical edge. Then I will do backtracking. So then this point, at this point I have first have to update my minimum. So minimum means low value, I have updated my low value. I have to check, is this a critical edge? Is the neighbor, is the neighbor of low of neighbor 0, is it greater than discovery time of particular node? No, this is not the case. So now let's move to next node. So I have this, I will discover at time 3. Then this is parent, I will not go here, I will go here. I will discover at time 4 and 4, 4 and 4. Then this is visited. Then I will update my minimum value. So I have updated to 0. Okay, this is parent, I will not update this, but this is my neighbor, this is already visited. Just take this low and update your low. So I have updated my low. Then just go to the next unvisited node. So I have here. Then sorry, I have missed one point. I have to check, is this a critical edge? If the low of neighbor is greater than discovery time of current node, no this is not the case, so this is surely not a critical edge. Then I will move here 5 and 5. Then what will I do? I will, this is visited, so I will update my low here. Is this a critical edge? If and only if low low of neighbor, low of neighbor 5, if 5 is greater than discovery, if so 3, if 3 is greater than 5, no this is not a critical edge. Then I will backtrack, and this is a crucial point, you will get it, why this will work and this will not work. We have to check, is this a critical edge? This is not a critical edge. As you can see, if I remove this, it will not break down the graph into two different components. So if the low of neighbor for 3 is 3 greater than discovery time of this node, so 4, no it is not. So this is not a critical edge. But if you check with this, if low of neighbor, which is 3, is it greater than your low? Yes, this is the case. So if you do this, and if you consider this, it means you are saying, if you remove this particular edge, it will break down into two different components. But this is not the case. So that's why the second, this thing will not work. Low and low will not work. You have to check, if the low of neighbor means if there's a back edge, low of neighbor will be updated. So if low contains greater value, means there's no back edge, not any other type of edge. So then only we will consider it. So there's a critical edge, there's a critical connection. So that's how this approach will work. Let's try to code this. So what we have edges list. So we have edges list. So first I have to create a graph. So this is my graph. Let me call it a list. Then we have this. So just add. Then for edges, just traverse in the edges. For connections, so this is a undirected. Then next thing we have is time. So this is a discovery time or a low time. Then another thing we have is low. Initially I will fill low to maximum value. So let me assign maximum here. So after this we also need a timer. At what time we reached a particular node. Initially timer value is 0. Timer. Then just apply your simple DFS function. First, what we need starting point, then we need our graph, and we need a parent. Then nothing else. We need to return this list. We need to find out edges, critical connections. So let's name it answer. So we need to initialize answer. Then just need to return the answer. So we have void DFS starting point, our graph, then parent. Then we first need to assign discovery time, DISC discovery time of starting node and low of starting to timer. Then after assigning this, we need to increment the timer for the next node. So just do this. Then traverse for neighbors. Neighbor, if neighbor is the parent value, so just ignore this. We are not interested in the parent. If neighbor is not visited, if low of neighbor contains maximum value, so just we need to traverse the neighbor node. So neighbor list and the current node, the starting node will be parent. Then we have traversed this. After traversing, we need to assign low and low point low low of starting will be low low of starting or low of neighbor. Then we need to check, is this a critical connection, critical edge? If and only if low of neighbor greater than discovery time of current node, then only we need to consider it. Add into the answer. What we need to add? Arrays dot as list A to B. So starting to neighbor, this is a critical connection. So let's give it a hit, and we have a error here. So this is a list. So this is edge. Instead of array, we have to treat it like a list. Then discovery cannot find symbol discovery because we have initialized it here. We have to initialize in a global variable discovery. Then we have low. So discovery, then low. So then we don't need this square braces, and we got discovery. So DISC, then arrays. We need to write arrays. Then we have some error. So error from 0 to 1, 0 to, okay. So if this is not visited, this contains maximum, then we need to do this. And uh, if this is not visited, then only we are treating it like this. But if the neighbor is visited, we also need to find low. So let's treat it outside. Let's write it outside. Then we got correct answer. Let's submit this. And now let's talk about time and space complexity. We are visiting a particular node only once, and we are traversing a particular edge only once. So the time complexity is v plus e, and space complexity is order of v. So the code is given in the description box. If you guys have any doubt, feel free to ask in the comment section. And thank you all for watching.